Hey guys, we have received multiple grievances about the sound quality of many of our previous videos from multiple viewers over a long period of time. We paid serious attention and as a solution, we are republishing all the episodes from our Verilog-A series all together in this marathon episode by digitally remastering the audio. In this marathon episode, you will learn from the basics to the advanced Verilog-A concepts with code examples. Once you complete this marathon, you will be professionally trained to handle and edit any pre-existing Verilog-A code. In this marathon episode, we will compare Verilog Digital with Verilog-A, which is used for analog design and verification purpose. Thus, you will learn the similarity and the differences between the digital and analog versions of the Verilog language. This is a must-have marathon for analog design and verification aspirants in VLSI. So stay tuned, stay focused. First episode on Verilog-A. In this episode, we are going to talk about why Verilog-A language was created, strong bonding between SPICE and Verilog-A, correlation of Verilog, Verilog-A and Verilog-AMS, basics of Verilog-A, modeling approaches along with examples. So let's begin. Why the Verilog-A language was created? It was created to face the competition from VHDL-AMS. OVI, the body that standardized Verilog, also standardized Verilog-AMS, a single language covering both analog and digital design. Verilog-A is a true analog subset of the Verilog-AMS language. High-level hardware description language. This is for analog designs. Now let's come to the SPICE and Verilog-A correlation and their dependency. We know that SPICE is a very widely used language for analog design. So SPICE is very good for transistor level analog circuit modeling, but it is difficult to model high-level system behaviors. Also, there is a limitation that SPICE model cards are dependent on BSIM, that is Berkeley Short Channel IGFET model, compact models. Original versions of BSIM models were written in C programming languages. Now let's come to an interesting point here where the Verilog-A comes into the picture, which joins SPICE and Verilog-A. All new versions of the model support only Verilog-A. This is, I am talking about the BSIM models, except BSIM 4 and BSIM 3. Now let's see which are the latest BSIM models. The various BSIM compact models available as per today are BSIM CMG, Common Multigate, that is used for FinFET technologies, BSIM IMG, Independent Multigate, BSIM SOI, that is used for FDSOR or UTSOI technologies, BSIM Bulk, also known as BSIM 6, it is used for bulk CMOS technologies, and BSIM 4, which is used from 0.13 micrometer down to 20 nanometer nodes. Now we saw that why these BSIM compact models are, which actually contribute to creating a SPICE model card. And nowadays, these all BSIM things are compact modeling is done by Verilog-A. So let's see a snippet how things are done inside a model card generation. So this is a snippet of Verilog-A definition for BSIM 4. For a MOSFET, we know that a SPICE model is defined like model name, the instance name, then the sequence of the nodes are DGSB, drain, gate, source and body. Then comes the model name that comes from the .lib model card, and the parameters, that is length, width, AD, AS, PD, PS. So these are basic things that will be there. These model parameters LW, AD, AS, PD, PS, this will be there for any model card. If you open a .lib containing the model cards, these will be the first things you will see. So let's see a snippet how Verilog-A is used for the calculation. So here there is a case is used for calculating the PS, PD, AS, AD. This is just a snippet, so the entire code is huge. So this way the Verilog-A compact modeling helps to generate the MOSFET model cards for our latest day SPICE models. So now come to talk about the Verilog-A and Verilog-AMS. Now, when we think of Verilog, first the language that comes to our mind is Verilog, which is used in digital designs. And in college, we usually get familiar with Verilog, that is for digital design. Now, the Verilog-AMS and Verilog-A, these are a highly professional area and they are mostly used in the industry. So let's see how the three languages are interconnected. Verilog. The simulations are discrete event or discrete value. The Verilog, it is continuous in time or continuous value simulation because it is for analog. Analog values will change with time. That is what we usually do in a transient simulation in SPICE, that with time being in the x-axis, another voltage or current being in the y-axis, and we see how the waveform changes with time as per the analog functions of the circuit. Signal flow architecture. I'll come later point what these architectures are. Conservative architecture. So there are two different architecture of Verilog-A modeling. One is a signal flow, another is a conservative. Now let's come to see what is Verilog-AMS. It is a superset of Verilog and Verilog-A. So the Verilog we know from the beginning and the Verilog-A that is used for analog, when combined together, no, not combined together, the Verilog-AMS will have something more. Support both discrete event and continuous time simulation. So in Verilog we have discrete event and in Verilog-A we have continuous. So both features are there in Verilog-AMS. Supports both system and circuit level modeling. Now comes the interesting part. There are extra features to AMS apart from Verilog-A and Verilog is number 1, discrete event and continuous value simulation. This makes compatible this Verilog-AMS to use both the Verilog and Verilog-A syntaxes for simulations. And mostly for this simulation what I am talking about is an analog digital co-simulation or analog digital mixed mode simulation. There are multiple terminologies spread over the industry, so anything you can pick up where an analog and a digital are simulated together. The second point is a very important part. Automatic interface element insertion. So interface element is a particular element that actually stays in the boundary of the digital and analog, and it helps to convert one into the another. Okay, here we cover the relation, correlation, interconnection of Verilog, Verilog-A and Verilog-AMS. Let's move on to the next slide. Before going further, as we know that Verilog-AMS is a bit different from Verilog digital. So what makes it different? Here, disciplines and natures are defined specific for analog circuits. Now, the discipline associate potential and flow together. The nature are the collection of attributes that can describe the units, absolute tolerance, convergence, and names of the potential and flow access functions. So let's exemplify. Here we will use a type electrical, which is actually a discipline. This discipline contains both potential and flow. Potential is voltage and flow is current. Now this voltage and current, how they are defined? They are defined as nature. Nature current is defined with the symbol, its unit and tolerance value. The voltage is defined as with the symbol, unit is volt and its tolerance. Simply, we also have power. Its symbol is PWR, unit is watt, and there is a tolerance. Now, these are different from the digital Verilog definition. So these discipline and nature, these are introduced in Verilog-AMS and these are used in Verilog-A, as Verilog is the subset of Verilog-AMS. Now, apart from these things, there is one more thing that is not present in the digital. That is temperature. Yes, analog circuit behavior depends on temperature. In SPICE, you usually define the temperature temp with the temp keyword. So here the nature is defined as temperature. Its symbol is temp and we can see the unit and the tolerance also. Temperature here is defined in Kelvin and the tolerance we can get here. So these are the new set of disciplines and nature that is different from the Verilog. And now let's move on to the basics. When we are talking about Verilog-A, let's now focus on to Verilog-A only. And for a while, let's keep apart the Verilog that is used for digital. So here in Verilog-A, current and voltage values are calculated simultaneously by Kirchhoff's laws. We know KCL and KVL from our college days. KVL, that is the potential around a loop, must sum to a zero. KCL is flows into a node must be sum to 0. So KVL and KCL are considered in Verilog-A. Values varies continuously with time. They are in analog nature. So when we see a waveform like this, we know that with time, it varies continuously. At this waveform, the value of the Y value is different at different time points, where time is independent in the x-axis. Supports both electrical and non-electrical signals. A new type of process, analog statement, is introduced here. This is a block that continuously applied. It's like a assign statement, similar to the assign statement we used in Verilog. Later we will see this analog block and we'll understand how it is continuous. This is the basic structure of Verilog. We have just talked about what the things are in there, and before that we have seen that what discipline and nature are already introduced in Verilog-A. Now let's see the modeling approach, means when we are writing a Verilog-A model, the approaches that we use. The first approach is a conservative modeling. Here, model relates potential and flows and the device modeling and loading at interfaces. So definitely there will be this thing. These are analog circuits. So these factors are considered here. This is called conservative modeling. And this is very similar to the SPICE modeling that we do. The difference with this, how we find in the next kind of modeling, is a signal flow modeling. Here in the signal flow modeling, we have two words, signal and flow, means flow of signals. So model relates to potentials only, and this is useful for abstract model. So here the flow will go from one point to another point. We'll come to the examples later on and this will get properly explained. And the third approach is that we can combine these two, the conservative modeling and the signal flow modeling. Let's move to the conservative modeling. With conservative systems, it is also useful to define the concept of a branch. A branch is a path of flow between two nodes through a component. Every branch has an associated potential and flow, and obviously there will be potential difference between the two nodes. So we can see in the picture here there are two nodes, and in between the two nodes, when we go from one node to another node, the thing is called a branch. Now let's see the nature of the node and details. A node is an interconnection point assumed to be infinitesimally small. No accumulation of flow on the node. No potential difference across the node. Branch, a path between the two nodes. No accumulation of flow on branch. So nodes where there will not be a potential difference, and in branch accumulation will not be there, but at the two ends we will see the potential difference. Let's understand this conservative modeling by a simple example. It's a resistor. So here two nodes are A and B of a resistor. Here we define these two nodes as electrical, and we also define a parameter called res with the value 1. Now here our analog block starts. This is the analog block that we are talking about in couple of slides back. Here the equation, and here less than, then the plus sign, this operator is called contribution operator. So here we can see the potential weighing between AB, or the branch AB we can say, is equal to resistor value into current between the two nodes A and B. So this is the resistor, simply V equal to IR, and the contribution operator here is a bit different. We'll see in the next example how it is different. So here our analog block ends, and this block will be in continuous in nature. So it doesn't just execute once and stops, not like that. It will be continuously operating, and with time the values inside this block will be executed and the results will be reflected. Here we close our module definition by the end module. The next example, RLC Parallel. Here multiple contributions will be used. In last slide, we talked about the contribution operator, that is less than and then the plus sign. It is called a contribution operator. It accumulates potential and flows to nodes, ports and branches. Order of contribution is not significant. So we can see multiple equations can be there in sequence, but overall effect will be taken into consideration, not the sequence. So let's see the RLC parallel circuit. We can see R, L and C. Let's define node A and node B. Now we will start writing the Verilog-A code. So module RLC, and our nodes are A and B. We define them to be as electrical. We define parameter R and exclude value 0. We'll see later a Y. parameter C equal to 1, parameter L equal to 1 and exclude zeros. These are the values of the resistor, capacitor and inductor. Now, let's begin the analog block that will define the behavior of this RLC parallel circuit. The first equation contributes the current for going through the resistor. Second one is for capacitor. In the third, this equation contributes for inductor. So we close our analog block here. Now we can see the IAB is common in the left hand side of the three equations, and this is I is the resultant of the three different currents that is happening in R, L and C. So this is the purpose of the contribution operator. It is accumulating the current, and the sequence is not important here. We can write the inductor first and then C and then R, or any of the permutation combination. Now let me also speak why we exclude 0. Here we can see in the first equation R is in the denominator as well as L is also at the denominator, hence we exclude 0. So this is how we excluded the case where divide by 0 condition. Now we close our module definition here by end module keyword. Signal flow modeling. So this is another modeling approach apart from the conservative modeling that we just talked about. So here in the picture we can see from A to B there is a flow and there is a potential is flowing. In signal flow modeling, signals may be potential, that is voltages, or flows, that is currents. Signal may be floating or differential. So floating is, we know, is a dangling condition, and differential is a mathematical expression. Signal flow and conservative models may be freely interconnected. So there is no hardcode boundary that we should make that this thing cannot interact with the conservative, not like that. The signal flow modeling and the conservative modeling can be interacted. They can interact with each other. So they can be mixed. Need for electrical modeling at the input and output. So when this is defined, we need to define some additional electrical modeling at the input and the output, the two nodes. Signal flow systems only have one potential associated with every node, that is one flow. As a result, the signal flow terminal must be unidirectional. That is the general nature of current. When the current flows, it flows in a direction at a particular time. It may either read the potential of a node or it may specify. So we are talking about A and B in the picture here. So here A and B. So when we talk about A, it reads, and here it defines the flow. Signal flow semantics require a smaller number of equations and unknowns, so results in a formulation that more efficient to simulate. Since this signal flow modeling is very less complicated, so coding is a bit simple. So let's see how. Here we are showing the example of an amplifier that has two ports, out and in. Input is in, output is out. We define these two as voltages, and we use a parameter called gain. Now our analog block starts, and V out is the contribution of gain multiplied by V in. So this is a very well-known amplifier equation, and if we change the gain parameter here, we will get different values of the amplification. So we end that block here. So this is very simple signal flow modeling, because here equation we can see there only the potential is flowing from in to out and it is multiplied by a gain. We close our module definition by end module. Hey guys, welcome back to the second episode. In this episode, we will be discussing inheritance in discipline and nature, data types of Verilog-A, branch and node declaration, analog block, assignment, contribution and implicit equation, 4 type of controlled sources, reserved keywords, constants and functions. So let's begin. We will be discussing some more on nature and disciplines, which we have not discussed in our previous episode. This particular page I am showing here just for a touch base purpose. This already I have explained in my previous video. In the previous page, we have used lot of attributes. Let's get familiar with them. Abstol, it specifies tolerance metric for convergence of potential or flow calculation. Access, the access attribute identifies the name for the access function. IDT nature, it represents the time integral. DDT nature, it represents the time derivative. Units, it specifies the unit for that particular nature or discipline. So let's move on to the derived nature or inheritance. This is the new thing that we have not discussed in our previous video. A nature may be derived from a parent discipline. So here we are talking about a parent-child relation, and let's see how this goes. This allows the new nature to retain or inherit the same attribute as the parent. The derived nature should include the discipline name followed by the hierarchical separator and the keyword flow or potential. So we'll see in the next example, and here I would like to mention that apart from whatever we are inheriting, we can definitely add something or change something. So let's see in the next example. Here, this is a parent nature. We have defined or named it as TTL current, and we can see its unit, axis and abstol. The next is TTL voltage. Unit is volt, axis is V, abstol is 100 micro. So from these two, we are creating the parent discipline here. This is discipline TTL, potential TTL volt, and flow is TTL current. So here we have used the parent nature that we have just discussed. Now let's see the derived nature. Here we have derived two natures. First one is TTL node current, that is TTL dot flow, as we mentioned in our previous slide. Here we have inherited everything as is. The next one is TTL node voltage, and here we have inherited as well as added or modified some of the attributes, like abstol is 1 milli and maximum value we have defined as 12.3. This is the new attribute for this nature. So guys, here we have seen the parent-child nature of the discipline and nature. Let's move on to the next slide. In this particular slide, I'll be giving an example of another type of discipline called ground. Yes guys, ground is a general ground of a circuit. So let's see the example. We use include the disciplines.vams that you generally do because all the discipline and natures are defined there. Writing the module name, defining the input and ground. Their nature is electrical, and we are specifying GND as ground here in this particular statement. We define the parameter here, resistance of a real value 50. Start our analog block by writing analog begin. Then we write the contribution statement here where we have used the ground also. We can see. Close this and close the entire module. So guys, this is the example of a type of discipline called ground. So next discipline is Wreal. It is used in real number modeling in analog as well as analog mixed signal cases. So let's get familiar. We include the file, write the module name, define the input, and we define the net type as Wreal. So this net will carry the real values. Real values in the sense that is the real data type. Output is out, and we define it as electrical. We start our analog block by analog begin, and we write our contribution statement that V out contributed by in, where in is a Wreal net, and it will carry the real data type value directly to the output. We close our analog block here by the end statement, and we close the entire module by end module statement. So guys, this is the example of usage of a Wreal discipline, and here by using the Wreal we can create a net type Wreal. In the next section, we are going to talk about all the data types in Verilog-A, integer, real, string and parameter. Let's see how they are. So string and real. Strings. Here we use range to create a string variable, and we can define the string variable here like in initial block string var equal to hello world, and we close it. And next the example is for real. So real is here A1 up to 64. It declares an array of 64 real values. It is a real variable and it's a vector variable. So here we defined a B, C, D. D is from 20 down to 0. Here we declare two real and an array of the reals. So guys, we have just seen how a real can be defined. Let's move to the integer and parameter. integer. Like previous one, we define integer as array. We can define it as an array A1 up to 64. And we can define integer as B, C, D and 20 down to 0. D is 20 down to 0. So 2 are single value integer and D is here an integer array. Parameters. So parameters plays a very important role in analog block. So just see, we define parameter by the keyword parameter, and the parameter could be any of the type, integer or real, anything. So here we defined as an integer. Another example. So let's see the parameter range specification. Now, what is a parameter range specification? When we define a parameter, we generally use it for a particular cause, and that particular variable could have upper and lower limit. Now, the upper and lower limit can have inclusive value as well as excluding values. So let's see how things are done. This triangular bracket means either of these indicate inclusion of the endpoints in the valid range. So if we define a range for a parameter and if we use this rectangular bracket, then it will be the included values. So the left hand limit and the right hand limit, both, or the lower limit or the upper limit, will be both included in the range. In this case, if we are using this first bracket or braces, in this case, it means that either of these indicate exclusion of the endpoints from the valid range. So, if we define a range and if we put this at in the lower limit as well as upper limit, that means the end values are not included. Combinations are valid. So, we can combine as we can see in the example. So, let's see the examples. Parameter here, the real parameter is defined from -15 as a static value and its range is specified by the keyword from. And we can see the lower limit is -50 and the upper limit is 0. Now, the lower limit -50 is included in the range while 0 is excluded from the range. It means that this particular variable or the parameter can have -50 up to 0, but 0 will not be a value for it. So let's see more examples. So in this example, the variable, it is an integer type parameter, integer type parameter. The 15 is particular value and its range is defined from 0 to 50, and neither 0 nor 50 is included as its value in the range. The next one is real and gain. Gain here, the static value is 1 and the range is specified here 1 up to 1000, and both 1 and 1000 are included in the range. So that means values can be equal to 1 as well as the value can be equal to 1000 and any value in between. In the next example here, we can see the parameter, real parameter type, and the parameter name is val3. Its present value is 0 and the range is from 0 to infinity, where the infinity is excluded from the range. And the exclude here, the values range from 10 to 20 as well as we exclude the range from 30 to 40. So in the first exclude, the 10 we are not including and 20 is also we are not including. But in the next exclude statement, we are not including 30 but including the value 40. So guys, let's go to the next example. So here, real type of parameter res 1 and it excludes 0. So let's move on to the next section and see more on nodes and branches. In previous episode, we have done a touch base on nodes and branches. Let's learn some more things on nodes and branches. Type of branches. A branch is a path between two nodes. If both nodes are conservative, then the branch is a conservative branch. It defines a branch potential and a branch flow. If one node is a signal flow node, then the branch becomes a signal flow branch. As we have seen this conservative and signal flow kind of modeling in previous video, so now we can relate here in the case of branches also. It defines either a branch potential or a branch flow, but not both. So let's look at the branch declaration. Here is a graphical representation of a branch from one node to the another, and we define here branch. And let's see how we can write a branch in Verilog-A syntax. example. So we define P and N node as in electrical of nature. Then we write branch. Then we write P and N the node and res the name of the branch. This is how a branch is defined. And we define here a parameter R equal to 50 of real nature, and we start our analog block by analog begin here, and we write the contribution equation here, and here we can see the V equal to IR equation, while instead of within the first bracket, within it we have not used the nodes, instead of we have used a branch res. So we close the analog block. So this is an example how we can define the branch in Verilog-A syntax. Now, let's come to this particular topic, branch declaration with vector. Here, we declare a vector net of voltage and it pipe down to 0. Name is vec1. And we also declare a vector net 1 up to 6 as vector 2. Now, the branch corresponding to this nets will be branch. How we'll define it? Branch, first the branch keyword, then within first bracket we write vector 1 and vector 2, close the first bracket, and then we write the vector branch name as vector branch. In contrast, if we want to declare a scalar branch, this way we will do it. We declare a voltage scalar net here, scalar net 2, and we declare the branch as branch statement, then first bracket scalar 1, scalar 2, and then the branch name as scalar branch. So let's see the analog block. In analog block, in our first video, we have shown how to write analog block by simple example. Now let's learn some more things. About the analog block, we can say that procedural statements are defined within an analog block. During simulation, entire analog block is evaluated. All the analog blocks are evaluated concurrently. So, say in our code, there are more than one analog block are there, but they will be evaluated concurrently, even though they may be either at the beginning or the end, but that is not their sequence. So, any number of analog blocks in our Verilog-A code will be evaluated concurrently. Indirect branch assignments can be done. Later we'll come to what is called indirect branch assignment. Analog signals are distinguished from digital signals in a way that they are derived from disciplines. So we have seen earlier that nature and disciplines are separately defined in Verilog-A to make room for the analog signals, which are very much different from the digital signals. While we are writing anything, the comments are very important because while coding, we have to keep the comments for description purpose. So let's see what kind of comments we use here. This is a single line comment with 2 forward slashes. This is an example of inline comment. So we can use it after we use the semicolon. We can use this as an inline comment. This is a multi-line comment. So let's move on to the next topic, types of analog blocks. So guys, there are two types of analog blocks. This is the first type. It is an inline analog block. So here we will write as analog, then the contribution statement, voltage between N1 and N2 is 1. This analog block represents a simple 1 volt source. So this is an inline analog block. Generally our analog block will be a multi-line. So this is a multi-line analog block. Here we start by analog begin. We write the first statement, and now we are using the conditional operators. Details about these conditional operators and loops I will be discussing in my next video. So I'll just go through it right now. So here the statement inside the if condition and the else. Inside else we are still using another if. And here the corresponding statement. Use the next else and use the next statement. So here comes our contribution equation and we close our analog block. So this is just a glimpse of a multi-line analog block just for your familiarity purpose or FYI kind of thing. So two type of blocks are there. One is an inline block, which sometimes we used for very simple declarations, like in this case a simple 1 volt source. And generally our coding will be the multi-line analog block where we define different conditions as well as contribution equations. So let's talk about the contribution. The contribution operator accumulates potential and flows to nodes, ports and branches their order of contribution is not significant. So in one particular analog block, there could be more than one contribution equation, but their sequence is not very important because when they are evaluated simultaneously. So let's see here, this is the first contribution equation where expression 1 is contributing towards voltage between node 1 and node 2. And here expression 2 is contributing to the voltage of node 1 and node 2. So in both the statements here are contributing to the same voltage which is between node 1 and node 2. Now this is equivalent to voltage between node 1 and node 2 is the contribution of expression 1 plus expression 2. So guys, this is the thing I was telling you, that when the accumulation operator is used, there could be multiple contribution statements, but once they are evaluated together. So we have described this. Let's move on to the next analog block, assignment. Assignment, let's see how we can assign something here. So it is here we have defined two variables. One is a R, which is an array of real number, and it is from 0 up to 3, and sum is a single or scalar real number. So we assign here with the equal to operator. The first value in the array R0 is equal to 10.1, R1 is 11.1, R2 is equal to 12.1, R3 is equal to 13.1, and then we assign addition of all these values to sum, that sum equal to R0 plus R1 plus R2 plus R3. Now we have seen assignment. Now let's see what is called indirect assignment. Few slides back I have just told that we will discuss about indirect assignment. So here is an example of an indirect assignment. Here we are using a double equal to operator, as well as we are using a colon between two different type of voltages. So let's see how we read it. This is read as find V out such that V in is 0. In this example says that output should be driven such a voltage that given equation is satisfied. This is called indirect assignment. So here we are not directly assigning anything, but we are making a condition that find V out such that V in is 0. Any branches referenced in such equation are only probed and not driven. So in this example, V in acts as a voltage probe. Now, here comes the most important point. Indirect assignments are incompatible with branch contribution statements. We have used in particular case a contribution statement, and in that particular case we cannot use a indirect assignment. So here let's see an indirect assignment example. This is of an ideal op-amp. So let's see the example. Here we declare the module op-amp. We define the output as well as non-inverting and inverting input. Output is out. Input are non-inverting and inverting. So we specify the directions here of the nodes or ports here. And we declare their type as voltage of all the three, out as well as non-inverting and inverting. Analog begin we write here. And we write the indirect assignment statement. Here V out is such that V non-inverting and inverting is equal to 0. So this means drive V out in such a way that voltage between the inverting and non-inverting is equal to 0. We close the statement analog begin, and that particular statement, the analog block is closed by end. And we close the module with end module. So guys, here we have just seen the indirect assignment example for an ideal op-amp. So this is one use. So let's move on to the next slide. So let's see what is an implicit equation. In general, we use a contribution statement like X is a contribution of Fx is called a implicit equation. So again I am repeating, X is a contribution of Fx. So in left hand side X is present and right hand side some function of X will be there. So this is called an implicit equation. So see an example here, module diode, and we defined A and C as electrical in nature. Parameter IS, parameter RS we have defined. Let's write the analog block. And here comes our implicit equation of the diode. We close the analog block and close the module. We can see here, let me draw the mouse pointer here. So here IAC is there in the left hand side, and here a lot of other functions are present, and inside that function IAC is present. So right hand side is acting as a function of IAC, while the left hand side IAC is there. So here like X is a contribution of Fx is satisfied here. So this is an implicit equation. So as I mentioned, the presence of IAC on both sides makes the equation implicit. Now let's talk about control sources. There are 4 types of control sources in Verilog-A we can define. Let's see what. First, the voltage controlled sources. The model for a voltage controlled voltage source is, first we define a branch. First branch is in and the second branch is out. And we define V out is a contribution of gain multiplied by voltage of the input branch. So next, the model for a voltage controlled current source is, first we define the branch, both the input as well as the output branch. And the contribution equation is I out is a contribution of gain multiplied by voltage of the input branch. So here we have discussed 2 voltage controlled sources. One is a voltage controlled voltage source and another one is voltage controlled current source. Now let's look into the current controlled current sources. The model for a current controlled voltage source is, first we define the 2 branches in and out, and we write the contribution equation as V out is a contribution of gain into I in. So now look into the current controlled current source. First define the branches in and out, both branches, and here I out is the contribution of gain into input. Here we have seen the 2 examples of current controlled sources, the current controlled voltage source as well as current controlled current source. Now let's have a quick look here for the reserved keywords. Guys, in any of the programming language or hardware description language, there will be few keywords, they are reserved and we cannot use them anywhere as any new kind of variable declaration or something. So let's see these things. Units. These we know comes as a unit suffix. We all know this. We are much familiar with these things. So this is kilo or K 10 to the power 3, whereas 10 to the power minus 3 is milli. Mega is 10 to the power 6, whereas micro is 10 to the power minus 6. Giga is 10 to the power 9. Nano is 10 to the power minus 9. So this way all these units are done and defined in Verilog-A. So we cannot use them for our own custom variable declaration or something, but they have to use in the way they are defined. So here are few reserved keywords. Some of them we have came across already, like abstol, discipline, end discipline, analog, ground, unit, IDT nature, DDT nature. All these are reserved, so we cannot use them for our personal purpose. These have to be used as they are defined. The reserved functions are like AC stimulus, analysis, white noise, last crossing. Details of these functions are available in the LRM. So I am not going in details here. Just for acknowledgement purpose, I am mentioning these names so that we never use these things as our own personal variable declaration or any module name declaration kind of stuff. There is another, it is called cross, transition is there. So here I am displaying some of the mathematical functions here like exponential, logarithmic, ln, mean, max, power, sine, cos, tan, arc sine, arc cos, arc tan. Okay, these are mathematical functions we know. Details of them are available in LRM. So we can get ourselves familiar with them from the LRM, but we should be very much cautious that we should not use them for our personal variable or module name purpose. Hey guys, welcome back. In this episode of Verilog-A, we are going to talk about Verilog versus Verilog-A comparison, control structures, loops and generate statement, predefined and user-defined functions, analog operators also known as analog filters, and analog events. So let's begin. So let's look at the comparison of Verilog versus Verilog-A. Guys, so far in last 2 episodes, we have talked about Verilog-A, and I assume that you already know the Verilog. So we can give a side-by-side comparison, few things which we find similarity as well as contrast between Verilog and Verilog-A. So here in this table, we are comparing Verilog and Verilog-A. So Verilog has initial and always block, we know, and similarly Verilog-A have analog block, which already we have came across in our last episodes. And there are few other things like initial step, crossing, timer, and final step, which we will discuss today. In Verilog, we have equal to and the less than equal to, these two operators for assignment. In Verilog-A, we have equal to and less than equal to and plus sign, that is a contribution operator for assignment. In Verilog, we have blocking and non-blocking operators. In Verilog-A, we have only concurrent contribution operator. These are just a glimpse how Verilog-A and Verilog are a bit similarity and dissimilarity. Let's look some more. Display functions. So guys, display function is like printf statement in C that we have in Verilog family. Okay, I'm not talking about printf, but here there are specific functions for this, like 4 functions in the leftmost column. We can see that strobe is there, display is there, write is there, and the monitor is there. And now let's compare in Verilog-A and Verilog what we have and what we don't have. Strobe, it is there in Verilog-A, it is there in Verilog, and it contains a default new line character at the end. Display is in Verilog-A, it is in Verilog, and it contains a new line. So these two are same to same in both the languages. Write is there in Verilog-A, it is in Verilog, and it do not contain any default new line character. Now let's look at the monitor. Oh, we do not have this $monitor function in Verilog-A, but we have this in Verilog, and it do have a new line character. So guys, this is a brief comparison that we have done between Verilog-A and Verilog with few points we have came across or we are going to cover. So let's move on to the next section. Control structures and loops. So in this we have if-else, case, repeat statement, while, for loop, forever loop, and generate statement. So let's look into all of these. So here is the if-else condition. So let's have a look with an example. If I greater than GA, the condition is written like this. Then we have result I, and more statements can come in here. Then we have else, and then we have result equal to J statement, and multiple statements can be here. So this is a rough structure of if-else structure that we use. This is a basic conditional statement that we use in any programming language. But for in Verilog-A, this is the kind of syntax that we are going to use. So let's have a look at the combination of if and else if. So we define a variable, a real variable value, and we write the first condition here. If value is greater than 0 and value is less than equal to 1, then we go to print run code A, and also here we can write the code A. In the next one, we have else if value is greater than 1 and value is less than equal to 2, we print run code B as well as we write the code B here. Similarly, in third else if we have value greater than 2 and value less than equal to 3, we run code C and we write the code C here as well. In the fourth condition, value is greater than 3 and value is less than equal to 4, and we print run code D, and here we have written the code D. And at the last, we write the else. This else is closing the first if. So here we write print illegal value with the strobe. So guys, this is the structure, and here this way we can use if and else if. So either if and else can be used, or if else can be used. Just to add another thing, that we can use nested if else, but I have not given any example here. We already know that nested if else is creating one if else loop inside one if condition, and that is more like we know from C language that how to create a nested if else. So let's move on to the next chapter, that is operators. So here, the operators that are in Verilog-A, arithmetic operators like plus, minus, multiply, divide. Modulus operator, it is used to get the remainder in a division, and the relational, less than, equal to, etc. And we have the not operator, that is logical negation. Then we have logical and, logical or, logical equality, logical inequality. We have more operators like bitwise negation, bitwise and, bitwise inclusive or, bitwise exclusive or, bitwise equivalence. We have left shift, we have right shift, we have conditional operator, or sometimes it is also called a ternary operator, and event ORing, which is a OR. So these are operators that we can use throughout the language, wherever the operators can be used. Like if we say that comparison things, right, in if or case, whatever. So these are the operators that we can use. It's a summarized version in this slide. Okay, let's move on to the next chapter. Case statement. So we know the case, and let's look how the case syntax has to be written in a Verilog-A code. So we again going to take the similar example that we have done for if. Here we define the real type variable value, and case we put 1, it's to be true. And in the first condition of the case, we write value greater than 0 and value less than 1, print code A. In the second condition, value greater than 1 and value less than equal to 2, print code B. In third condition, value greater than 2 and value less than equal to 3, print code C. In fourth condition, value greater than 3 and value less than equal to 4, print code D. So up to here we see that the 4 case conditions, we can deal with the respective code. Here we have used only the print code, but we can have the actual codes here also. Here, the speciality of the case is that we always have a default condition. Here the default we give here a print condition error please check value, because once the value is the outside of the range mentioned in all 4 cases, outside of all these 4 conditions, then we print a error message here. We end the case with the end case statement. So here we are done with case. Let's move on to the next chapter, the repeat statement. Repeat statement helps to run a block of code for a fixed number of time. So it repeats a block of code for a fixed number of time. So let's look at an example. We define integer I and total. Initialize I with 0, total with 0. Repeat 10, that means it repeat 10 times. We begin the repeat block. We write I equal to I plus 1. Total equal to total plus I. We end the repeat block here. So we can see here the repeat block will repeat 10 times the code written inside its body in between begin and end. So we know the iteration will happen only 10 times. So let's look at the while loop. Here we also see through an example. We define integer random number and counter, and we define the random number. Counter we initialize with 0. And while random number, we start with the begin. This actually starts the body of the while. Counter equal to counter plus 1. Then random number equal to, again, we are defining it. And then end. So we close the body of the while loop. And at the end, once the while loop is done, we are outside the while loop. We use a print statement to print the counter value. So guys, here we are exemplified one while structure here. So I think we are done with the while loop. Let's move on to the next chapter. For loop. Again another example, and here before going through any further, I see that for loop is like the C style, so you can easily relate with C style for loop. We write here width equal to 20 and we start the for loop, and we initialize k with 1, k less than equal to width and k equal to k plus 1, and we begin the body. And we write all the statements that are necessary for us inside the loop, and then we close the loop. So this is the structure of the for loop that we can typically use for a for loop, which is a C style here, and begin and end defines the body of the for loop. So we are done with this particular loop. Let's move on to forever loop. Forever statement helps to run a block infinite number of time. So guys, I hope you remember when we learned the C code, we generally come sometime in a situation that our for loop went for an infinite loop. in HDL sometime like Verilog-A code, sometime we may need this particular infinite loop, and it is for our ease, it is defined there. And let's see with an example. So forever we write here because it's forever and we don't have to put any condition here. We immediately begin the body and we write the code here with all of the statements. And we end the body with the end statement, the forever statement. So this helps us to make some code that is running for infinitely, independent of time. It will run inside the analog block. Just to like a guesswork here, we can have a clock-like statement inside this forever, where the clock will generate some PWL kind of stuff and it will operate forever. Such kind of application may be done through forever loop. So we are done with this. Let's move on to the generate statement. So what is a generate statement? Before going to the details, I would like to exemplify it because the generate statement repeats a particular block of code, but the usage is different. And this thing will happen during the elaboration time, compile and elaboration once it is done. So without any delay, let's look at the example. Here with the directive, we define bits with 4 and we write the module name. Here we define input, the output is a vector here, and we define the nature, both input and output. So and we'll define the parameters like delay, transient time, full scale, etc. And we define the real variable here, sample and half. And we write the body here. So I'm not going to the details what is the equation here, just because to exemplify the generate statement. So let's start with the generate statement here. We have initialized all the variables and etc. in the analog block. In between the analog block and the generate, we have defined the necessary things here. And let's look at the generate statement here. So generate statement will repeat itself, but how? It's with I, and I will run from bits -1 down to 0. So I is an integer here, and it will start counting from bits -1 and it will count down up to 0. And so we begin the block. So you can see here that V out is a vectored node. So here we use the contribution operator here to define it. Here comes the conditional statement and we end the generate here. So our generate block will use these 3 statements and it will flatten the parametric way of defining that V out and I to an explicit one time of after compilation and elaboration. Let's end the module here. So first we ended the analog module and then the actual module here. So this is our target code which will be flattened using the generate statement because it's in a parametric form, and the parametric form of this vector is controlled by the variable I, and range of I is bit -1 down to 0. So let's see how it looks once it is flattened. So after compile and elaboration, this generate statement will expand like in the analog block. Okay, these are the equations. Now this is the first one, V out 3. These 3 lines are coming together because they are repeated, or you can say flattened from a parametric to a explicit form. And here we see that V3, V out 2, V out 3, V out 1 and V out 0. These are flattened and here the analog block ends. So this is the generate statement. So through this example, you are able to understand what the generate statement is and where we have to use its purpose. So let's move on to functions. So functions, we know that will have some input and there will be a block which have some code and we then get the output. So this is functions. Guys, let's look at the user defined function. Here we are going to define the prototype or show you the prototype. This is not an example. This analog function is, the first line will be the analog function. This is a keyword, and then the next is return type, real or integer. Then next one is the function name. And then we define the inputs in the input declaration section. We start the body with begin keyword. Here we write all the statements in the statement block. We end the body by end keyword, and we end the analog function with the end function keyword. So guys, remember this input declaration and statement block. These are 2 blocks. This is not a single statement. The statement block, let's look, can use any statements available for conditional execution. That means any conditional execution, and can only reference locally defined variables or past variables arguments. Must have at least one input declared. The analog function implicitly declares a variable of the same name as the function, that is function name. This variable must be assigned inside the statement block. Its last assigned value will be passed back. This will be the return value. We have restrictions also. We cannot use access functions, cannot use contribution statements or event control statements. We cannot use any named blocks. Let's look into one example here. Function, the return type is real, then max v. We write input n1, n2, electrical n1, n2. These are the natures of the input. We start the body. We write here max v is equal to vn1 greater than vn2. If this is true, max v will be vn1, otherwise vn2. So this is a ternary operator. We discussed this operator few slides back in the operator slide. And we end the body here. And we end the function with the end function keyword. Now comes the section of the calling of the function. So this is the function we have defined and how we will call the function. So we write BC29, it's a voltage, and we give the max voltage C36 and C1. So these are two nodes we have given. These node voltages will be passed on to there, and the maximum voltage will be returned to BC29. So this is how we define user-defined function in Verilog-A. We have given all the details, and as well as this is the example. Let's move on to predefined functions. So Verilog-A has some predefined functions like real time. It returns the present simulation time in second. $temperature gives the ambient temperature in Kelvin. $VT, it is the thermal voltage KT by Q, and $VT temp is the thermal voltage at a given temperature. So these are predefined functions. In this section, we will discuss about the signal access functions. So here the first one is VB1. We know this is the voltage across branch B1. VN1 is a voltage of node N1 with respect to ground. Now guys, look at the two things. They are written in a similar way, but B1 is a branch. We discussed branch in our previous episodes. And the second one is of a node, or it could be a port also. But here the voltage is measured with respect to the ground. The third one, VN1, N2, is the voltage between the two node or ports N1 and N2. The next one is current in branch B1, IB1, and the next one is IN1, the current flowing in node 1, N1 to ground. So these two are also look very familiar in type of writing, but these are different because the first one gives a branch current, the second one gives a particular node current which is from that node flowing towards the ground. The third one is IN1, N2, which gives the current between the two node or ports N1 and N2. So these are the signal access functions. So we are done with this section. Let's move on to the next section. Analog operators. These are also known as analog filters. So let's look what are the analog operators. Analog operators operate on an expression and return a value. The expression and the return value may be either a scalar or a vector in nature. If the expression is vector valued, then the return value will be vector valued with the same dimension. Analog operators are also referred to as filters as they include the time derivative, time integral, and delay operators from calculus. They also include transition and slew filters that are used to remove the discontinuity from a piecewise constant and a piecewise continuous waveforms. So these are from digital, right? So they will be converted to an analog one with this transition or slew filters. Restrictions for analog filters. Analog operators can only be used inside an analog block. So we are defining a module and we cannot write these filters outside the analog block. We have to define them inside the analog block. Analog operators must not be used inside conditional statements. So like if, else, or case, this kind of conditional statements, inside them we cannot write them. Analog operators are not allowed in forever, repeat, while, and for loop statements. Analog operators are allowed in generate statement. So guys, generate statement we showed example few slides back. We can use this analog filters inside the generate statement, but not on forever, repeat, while, and other things. They cannot be used inside a user-defined function. So inside the user-defined function, anywhere we cannot use it. These restrictions are present to prevent the corruption of internal state and hence the anomalous behavior. So guys, these restrictions are there. It's for a good, because if they are used right, they will corrupt the internal calculation and the anomalous result will come out for a particular variable node or whatever we are using. So we have to follow these restrictions. This is a delay operator. We are going to now what operators and all other layers. The first one is the analog delay operator. So delay implements the transport delay for a continuous waveform. Expression is delayed by the amount time delay. So this is the type of expression. So result equal to delay, then the expression itself on which we are applying the delay and the time delay value. So this will add the delay, that is a time shift, in the resultant expression. Another way of expressing is that result delay, then the expression, then the time delay and the max delay. Okay, let's look on to the details. In the first case, time delay value is used and to add a delay. In the second case, time delay is already defined by the time delay and can change up to the max delay. So we are giving an upper cap, that is max delay, up to which this value can be changed. Another similar operator is absolute delay operator. So absolute delay operator, abs delay, is used to provide delay for a continuous waveform. So here we use the absolute delay, expression, then time delay. The second one is where we use the maximum capping, the max delay. Example, how we use that: V delayed is equal to abs delay of V in and then the time delay. The next operator is a transition filter or transition operator. Okay, so let's look into it. The transition operator, the syntax is result is equal to transition, then expression, the delay value written in green, then rise time written in blue and the fall time written in orange. So this way we will define the transition operator, and let's look graphically how this thing will impact. So the top waveform, here we bring the mouse pointer. This is the digital waveform. Here we see it is sharp changing, then it is flat again coming down. So this node, if we add a delay, right, so it will shift here. This is the time shift or the delay is added. Then this straight up is changed to inclined with the rise time. So we will specify rise time will come into effect here, and then the flat is there, and then again the fall time is specified here, will govern the falling of the signal with the slant. Okay, and this node is here. So this is how we are defining. So let's get some more details. So the transition filter is used to smooth out the piecewise constant, sometimes we call it PWL waveforms. Delay is the delay amount and must be greater than equal to 0. The default is to be 0. The rise time is the transition rise time and it must be greater than 0. The fall time is the transition fall time and must be greater than 0 or it equal to 0. So next operator is slew operator or filter. So this is the syntax that we use for the slew filter. Slew, here the first one is expression, then the max positive slew rate, then the max negative slew rate. So here is the waveform which is rising, and we define the slew by delta y by delta x. The slew filter provides a means to bound the rate of change of a waveform. So we just shown in the adjacent figure the rate of change. Okay. Expression in the first syntax, right, is the input waveform expression. The max positive slew rate is the maximum positive slew rate allowed, that must be greater than 0. And maximum negative slew rate is the maximum negative slew rate that is allowed, that is less than 0. So here how we define the slew. Okay, we are done with this particular operator. Let's move on. And we come to the next section. So let's talk about analog events. And here we see there is a ampersand sign. Okay, so wait for where it is used. The analog events is the analog behavior of a component that can be controlled using events. Events have characteristics of no time duration, and events can trigger and detected in different parts of the behavioral model. Events are detected using the ampersand operator. Global events. These are initial step and the final step. So initial is for the initialization and final is happen at the final. So we are starting a simulation at the initial step, we can do something with the initial step. At the final, when the simulation is stopped at the last time step, we can use the final step and it will control the things at the final step. Monitoring events. So these are cross event and the timer event. The cross event and the timer event. Cross will handle the crossing of a signal and the timer will insert a particular time related stuff. So let's look into. So here initial step, it is event triggering at the initial step. So as I said that at the starting point of the simulation, initialization have to be done by this initial step. So here the syntax is @ then parenthesis initial step and then will be the type of analysis. So I'll come to the type of analysis. It's like DC, AC, transient, like all those stuffs or noise. The final step is event triggering at the final step and the syntax is @ final step and the analysis type. Then comes the cross, zero crossing threshold detection. So we are saying about a particular threshold line. Pictorially, I'll exemplify it later. So this will be the syntax cross, then expression direction, then time tolerance, then expression tolerance. Then at the timer. So generate analog event at specific time. Timer, the expression is like timer, then the start time, then the period and the timing tolerance. Okay, let's look at initial step and the final step. So initial step AC, DC, anything will be active for AC and DC analysis. Here we can use multiple types. So this is for initial AC and DC. So initial step transient. It is active for transient only. The first one was active. This initial steps will be active for DC and AC both. But the second one is for transient only. The final step here, it is for active only for noise analysis. And the second one is active only for transient analysis. Available analysis types. So here we define the analysis types AC, DC, transient, noise and unknown. So guys, here we just exemplified that initial and final steps and their analysis types. Analysis types are the type of analysis that we are doing with the analog circuit like AC analysis, DC analysis, transient analysis, noise analysis, like that. Let's look at the initial step with an example. We start a test bench module here. We define the electrical AB, in out AB, okay, and then real, and we define some vectors here. So here y, x and fxy. So fxy will come later. This is a function of xy. And we start the analog block with analog begin, and then we write the initial step and we start the begin. Okay, so each element of those vectors are now getting defined, y0, x0 and fxy0. Similarly, the index 1 here, we define all index 1. So this is how we are defining a lookup table here for the function xy for the x and y. We keep on defining for the elements here in the initial block, and then we come at 0 to 11. We are done for the definition. So we have defined the lookup table of the function xy for various x and y values. And here we close the initial step definition. Okay. Here we write our contribution statement and we close our analog block. So we close the end module. Here we define pictorially the right hand side graph. It gives the fxy graph for the two independent variables, that is x and y, and that $table model used in the contribution statement is an interpolation function that will do the lookup in the table. When we define a function, we are not going to change this lookup table anywhere in the rest of the code. So we put this data here in the initial step. So this is the purpose of the initial step, just to initialize the value. Those are we are not going to change or getting used in the later point. So these are for initialization. For this particular example, we are not changing the values. We will be using the values. But there could be cases where we can initialize a value and later we can, as per the demand, we can change it. This is the purpose of the initial block, initial step block. Let's look at the cross, @ monitoring event. So this is the syntax: cross, then expression, then direction, then timing tolerance, the expression tolerance, and then enable. So here just we see the signal that is going up and there is a threshold that is defined by a horizontal line. So we want to see when this signal, because the analog signal is a continuous and it is not discrete like the digital, it is a continuous. So we have to measure some point where this signal is crossing this defined threshold. So how we write this, just to exemplify here: analog begin, then cross, V sample minus 2.5. So guys, V sample is the signal that is changing and minus 2.5. So once we equate that V sample minus 2.5 equal to 0, what we get? That V sample at particular time when this threshold of 2.5 is crossed. And the next argument is +1. So that means the signal is changing in a positive direction. So it is going upward as per our left side figure. Then we write the contribution statement. According to this particular cross, what we are doing action is done by the contribution statement, and we close the analog block. So this is a short and sweet example of a cross. So let's talk more about the direction operator. So if it is set to 0 or not specified, both positive and negative crossing will be taken into account. If the direction is +1, then the rising edge transitions will be considered. If it is -1, then the falling edge transitions will be considered. So guys, this is the cross function that we use in analog block. So we are done with this one. So let's move on to the next one. That is the @timer, time point specific event. So let's look at the syntax. It is timer, then start time, then period. The timer function is used to generate analog event to detect specific time points in time. The timer function schedules an event that occurs at start time. If the period is specified, then timer function schedules subsequent events at multiples of this period. So the timer block will have some code. It will initiate at the start time. If period is specified, then it's gonna repeat after that particular period. So let's look into an example. We start the module. We define the output, then the parameter, then the integer, and we come here for the analog block. Here we write @timer, then 0, and then the period. Period is defined already by the parameter period, and it is initialized value for this parameter is 1.0. So here the timer block, let's see what it will do. It will set x equal to random plus 0.5. This timer block will start at time 0 as 0 is specified, and then at the interval of each period this is going to execute. So here we write our contribution statement and we close the analog block. So here guys, we have just defined the definition of the timer has been given, and the example also is given here. So this way we can use a timer block. And finally, we close the module here. For the timer here, I'd like to emphasize one thing. Just the line immediate to it is there, contributes to the timer. If we have to write multiple statements, we have to use the begin and end for this one. So let's look into an example where we have used initial, timer, and final. So we define the inputs and integers input, and we define the parameter with period and threshold. Okay, analog begin. This is the initial step, begin. We initialize bits and errors with 0, initialize the variables. We end this with end. Timer, then we have begin and end. We write an if statement here, and we close the timer here. Next, we come at the final step. We just here print this bit error rate, and we end the analog block. And finally, we close the module with the end module definition. So guys, here the initial step, the timer, and the final step are shown in a single example. So you can see in what style this can be used. So I think rather than giving a definition, the example clears out your mind how these things can be done and easy to digest for you. Welcome back guys. In this episode, we'll be discussing above event, last crossing, and event ORing, dealing with the discontinuity, structural modeling using Verilog-A, pre-processor directives, and we'll look into the point where Verilog meets Verilog-A. So let's begin. Let's talk about the above event. The above function generates an event at the time when a specified expression becomes greater than or equal to 0. So this is the syntax of the above event. The first argument is expr, then the time tolerance, then the expression tolerance. So expr or the expression is a real expression whose value is to be compared to 0. Time tolerance is the value of the tolerance value of the time interval. And expression tolerance is the tolerance value of the mentioned expression. So let's see an example to understand how this above event can be used. To include our discipline.vams, we use a preprocessor directive define and define high as 1, define low as 0, and we start our module, a test module. We write electrical in and out, then we define parameter of real type, VTH high as 3, VTH low as 1, and then we define another real variable as out value. Then we start our analog block with analog begin. Here we write the above statement, and inside the above statement is Vin minus VTH high. So this value has to be compared with 0, and whenever this crosses, this condition will be evaluated. And once this is true, we assign out value with backtick high. And similarly, we define the next above statement here with the inside expression is VTH low minus Vin. So once this is true, we set our out value as backtick low. And outside all this above statement, we assign finally the out value, which is a real variable, to Vout. And we close our analog block here. And then we close the end module. So in this example, we exemplify how we use the above statement. So let's move on to last crossing. We have earlier used the cross. This is whenever multiple crosses are there, this will detect the last one. So the last crossing function finds the time when the signal last cross 0. The expression is last crossing, then expression, then direction. The first argument is a signal expression. The direction is a flag with 3 possible values is -1, 0 and +1. If the direction is 0 or not specified, the last crossing will be detected on both rising and falling crossings. If the direction is +1, the last crossing will be from the last rising edge. If the direction is -1, the last crossing will be from the last falling edge. If the expression has not crossed 0, the function will return a negative value instead of a time value. So, if in the execution of our Verilog-A code, we see it has returned a negative value, that means the expression has never crossed a 0. So, there is neither a rising nor a fall crossing at all has happened. So, in that case, we have to check our waveform on which we are operating this last crossing. So, let's see an example of this last crossing. We define a module. We declare the all inputs and then the integer. Input is in and it is of voltage type. Then integer we define crossing, real as latest and previous. We start our analog block. We write the initial. So in last episode we seen the definition of the initial step. Here we are using it. We initialize the value of crossing and previous with 0 here. We close it, close the initial step block. Then we write the cross and then we write the expression Vin and we give a direction +1. And here we assign, if it is a +1, and then we write crossing equal to crossing +1 and previous equal to latest. So these are the two assignments we do here, and then we close that block with end. Then we write that latest is equal to the last crossing, the function that we already just now discussed, and Vin is the first expression and then the +1. Then at the final step, what we do, if crossing is less than 2, we could not measure the period. So here, let's see the next print statement here. Here comes the else condition. Else the period and the crossing will be printed here. So once this crossing has happened more than once, then we will be able to measure the period, and in that case, this period and crossings will be printed. And we close the final step block with end. And we close our analog block with end, and then we close the module here. Guys, this is the example of the last crossing. This is specific to get the last crossing, and it can be used with the cross statement. Okay, let's move on to event ORing. We can do ORing. Events we have already discussed in our previous episodes. So here we'll see how we can OR two events. So we'll do this with an example. We write the analog begin here. Then we write @ then initial step or cross. Then within the cross we have the expression V sample minus 2.5 and the direction is +1. So here we write the contribution statement V out, 0 is contributed to V out. And then we close our analog block. So guys, here we can see that we can use the two events with the OR statement. So this the initial step or at the cross, whenever it is there, 0 will be contributed to the V out. Let's talk about discontinuity. So discontinuity and the expression will be constant expression. Now, what is a discontinuity? Just before going any further, so discontinuity is a nature of the circuit. In that circuit, since the analog is a continuous in nature, right? Time when we vary any signal in analog, that signal will be continuous. For each time step, we will be having a corresponding value. But in some of the cases, it could be that the equation or the circuit may be discontinuous at some of these time points. So keeping that thing in mind, we have this discontinuity expression. So let's see about discontinuity. This function is created to deal with any possible discontinuity in analog behavior of the circuit. That is what I just explained, that any circuit can have a discontinuity based on its equation, the mathematical equation. So discontinuity is only executed whenever the analog behavior changes discontinuously. Already mentioned, there are continuous changes at some time point, there is a discontinuity, and then there is another time point when after that the signal is becoming continuous again. To deal with this situation, the discontinuity enables to the simulator the handle of the convergence algorithm to get accurate result in exceptional situations. So we know that any simulator use numerical methods inside it to deal with the convergence, and if there is a discontinuity, it might cause an issue of the convergence, and this discontinuity function will help or to instruct the simulator to make the convergence better, because it's an analog design and we know how and when the design will behave, and we'll already know at some point that okay, at t equal to t dash our circuit will be discontinuous. So we define this discontinuity well ahead so that the simulator do not struggle to converge. So discontinuity is 0. It is 0 in the argument, right? It indicates a discontinuity in the equation. Discontinuity with value 1 indicates the discontinuity in its slope, etc. Discontinuity minus 1 is used with the limit function. So minus 1 is also a valid argument of discontinuity, the limiting value function. So guys, we have just came across or have the concept of discontinuity in analog and how we can deal, and we have just theoretically explained here. Let's see an example. We write here the module name, and we define all those inputs. So in out is P1, C2, input is PIN, NIN, and we define 4 ports as electrical in nature. We define a real parameter with 1 value, and we start our analog block, and we write here cross, with the cross event, we write here the discontinuity 0. And then we put the conditional block here, and we close our analog block. So this way we can introduce a discontinuity with the event itself. Let's close the module here, and this is the example. So this discontinuity is not that mandatory we have to define, but in certain cases we know in analog modeling, right, this circuit is discontinuous. We certainly know in that case we will have to define. So let's see another example of the discontinuity. Here we define the module and define the output here, and it is a voltage type. Then we define the parameter of real type, period and amplitude, and then we define the integer slope, real offset. Then we start our analog block. Then we write timer event with the argument 0 and period, and start the timer block, and then now we write the statement slope equal to +1. Then we set as offset is equal to real time. So real time is system defined function, and in previous episode we have discussed about it. And then we write the discontinuity 1. So this discontinuity 1 we just talked about 2 slides back. We close the timer block here. Then we write another timer block with the initial value of period by 2, and the period will be period. So it is different from the first one. In first one that initial point was 0. So then slope equal to -1, offset equal to real time, and we again say discontinuity 1. So we close this timer block. And then once these 2 events are done, the timer blocks are done, outside that we write contribution statement. We close the analog block here and close the entire module here. So these are the 2 different way of using a discontinuity. Definitely the example, obviously these are not exhaustive, but obviously when we are dealing with analog design, we will keep in mind that discontinuity is a factor that we have to be very cautious. Otherwise the simulator will struggle and may diverge. So let's see the next chapter. structural modeling. Okay guys, so this is the very important chapter because so far we have discussed about different features of Verilog-A and we have seen several examples, but at the end when we have to design an analog circuit, right, we have to define different blocks and we have to interconnect them. That is called structural modeling. So let's see, in Verilog the structural modeling is already there, and in Verilog-A let's see how we do it. And we will do it by an example. So here is our circuit. Here, this circuit, we can see there are two sub blocks, VD1 and VD2. I'll come to later, but the input and the output, what we'll do, that input QIN will, whatever voltage we give, and Q out will give the 4 times of this voltage. Now we come down to VD1 and VD2. These are two voltage doublers. So these two are connected in series. The first one doubles the voltage, and that double voltage is again doubled to get a 4 times of the input voltage at Q out. So let's see. We define a module voltage quant and we define the input and output, and they define their nature as electrical. Then we write also the where AA1, that is used for interconnection, and we use the voltage doubler unit here, and its instance is VD1 and we know it's 2 input Q in and the output will be AA1. And this AA1 goes to the next voltage doubler unit VD2, which is the instance of the voltage doubler module, and then the final output is Q out, and I close the module here. So now just look into this. In this design I am going from the top to down approach, but now we can define this voltage doubler in Verilog-A. So we write the module voltage doubler, we define in and out, nature is electrical, and we write the analog begin block here, and we write here V out is 2.0 into V in. This is the contribution statement. So this is a signal flow modeling. By looking at this, you can guess that this is a signal flow modeling. This particular voltage doubler unit I am saying, and this expression we make a voltage gain circuit, and we close the analog block. So here we can see the V in, whatever it is getting doubled at V out, and we close the end module. So this entire example gives you a very simple structural modeling using Verilog-A. So whenever we are doing any modeling in a structural way in analog circuit, definitely we'll have different blocks. In analog circuit, we have different blocks, and those blocks each we can define in Verilog-A, and then we use interconnection of where to interconnect them. So this way we can use structural modeling to create a bigger circuit. So guys, here we come to this end of the structural modeling. So let's go to the next section, which is preprocessor directives. So this preprocessor directives, we know it's like we generally learn C as a first programming language in colleges. Usually we are very much familiar with this preprocessor directive because at the first line we have to write this preprocessor directives. So similarly in Verilog-A we have couple of preprocessor directives. Some of them we use very often and some of them are in situation. So let's see what are there. We will talk about define, undef, if-def, else and include. So let's first talk about include and defining macros. So include, we can include a file name. This is the first thing we write in any Verilog-A code is the discipline.vams. I have discussed in the first episode about this discipline.vams, and also we include the constants here. So this two include statement becomes very much important in any Verilog-A code. So the next is we define, it is a macro, okay, the define pi with 3.14. So we know that whenever in the circuit description the pi is used, it will be replaced by 3.14. So this is very much C-like thing. So we can easily relate. So then we write, okay, this is the examples. What happens that this contribution statement in the right hand side, we have pi, sorry for the discolor thing. And here whenever this equation is elaborated, right, before execution, obviously we'll do the compilation and elaboration. And in that stage, this pi will be replaced by 3.14 in the actual equation. So define another way of define an inline function like this, define the sum AB, which will result with A plus B. And here if this goes, V out is a contribution of backtick sum V in 1 and V in 2. So this will add the two voltages and will be contributed to the V out. So this is a typical Verilog-A example of a inline macro. It is not a function, it's a macro, so inline macro. So this will be used or it will be replaced during the compile and elaboration time. So conditional macro. So let's see some examples. So it's a if-def, we define a macro name and then the first if statements are there. then we end it with end if. So this is a simple if condition in the preprocessor directive. Okay, and let's see now the if else combination. So if def the macro name, then the statements, then the else comes and the else statements comes, and we close it with a end if equation. So these are conditional macro. In some cases with maybe system variables or something, we have to initiate something in our analog module, we can use these things. Okay, so if the system variable is something, then we do something, and if it is variable value is something else, we do something. For that we can use this if def else and end if structure. Let's go to the next section, which is boundary. Boundary of what? So Verilog and Verilog-A. So far in our last episode, we have discussed the comparison of Verilog and Verilog-A. Here, we will be talking about the junction of Verilog and Verilog-A. So let's see at junction what things are there. The connect modules. So the connect modules actually connects a Verilog-A block with a Verilog block or vice versa. A connect module automatically or manually inserted to connect the continuous, that is analog, and discrete disciplines, that is digital or mixed nets. A connect module contains the code required to translate and propagate signals between the analog and digital components. So, the disciplines of mixed nets are determined prior to the connect module insertion in phase of elaboration. So, let's see some of them. So here we will be discussing about a D2A. So that is digital to analog. Here the connect module and how we write the code. Here how these are defined. So I am not saying how we write in our code, but how a connect module D2A is defined. So it has in and out. In is a input, out is output, and input is a logic in nature, and output is a electrical in nature. So guys, look that the input is logic, so it is digital, and output is electrical because electrical is an analog nature. So connect module, it is defined in such a way that input is digital and the output is analog. And we end the module with end module. So this is a basic inside look of the D2A Connect module. By looking into this code, we understand that if this module, this connect module is inserted between a signal which is going from a digital to the analog, we will definitely able to carry the signal in a proper way. So it is crossing the boundary of a digital and analog. So it is from digital side, it's crossing the boundary and entering into the analog side. So let's look at the A2D. So here is the connect module. We write A2D out and in. Okay. So out will be output, in is a input, and output is logical and input is electrical. And then we end module here. By looking into the inside structure of a A2D Connect module, we understand that whenever a signal is traversing from analog side to the digital side, obviously this connect module will help to balance the two things. So the input will be electrical, which is analog, and the output will be a logic. Let's talk about the bidirectional, that is BD, this connect module. Let's see what the structure is. We have out and in. So we have in out. We have in out both for input and output. So it can be bidirectional. So the logic is out and electrical is in the module with end module. Here in this case, the signal can go from any direction to the other, provided we are connecting in a such a way, we are connecting the input port in an analog side and we are connecting the output port in a digital side. But the signal can travel from either side to another side. So this is a connect module which can be inserted or it is automatically inserted. It depends upon simulator to simulator for a mixed signal structure. So guys, so far we have seen the connect modules and let's talk about the connect rules. So connect rules and the discipline or the mixed signal, that is analog and digital, can be used to control the auto insertion throughout the hierarchy. So let's see just an example, because what I am saying that this is the boundary of digital and analog. If the discussion is further, will enter entirely from Verilog-A to the Verilog-AMS, where the mixed analysis or mixed mode simulation of Verilog and Verilog-A can be done. So we are at the boundary, so we'll not cross the boundary. So within the boundary, we'll just have a glimpse that what are the connect rules. So connect rule is the example. And first connect rule is D2A and we define all of its input and output structure. Okay. Then the second one is A2D and we define similarly. And bidir, we also define it. and then we end the connect rule. So this way, these connect rules are done for a mixed mode simulation. We'll be stopping here because this tutorial is for only Verilog-A, and we'll be not discussing anything on Verilog-AMS here because this series is intended for the Verilog-A. So thank you for listening carefully and hope you enjoyed it.